Okay. Well, I wanted to talk for a few minutes about Einstein at home. The idea for this actually came in a lunchtime conversation in 1999. Myself and a friend had read an article in the LA Times that day, which was about SETI at home. And we thought this would be a great way to get computer cycles for a data analysis problem that we had, but we didn't think anybody would be interested in it. It wasn't nearly as cool as looking for extraterrestrial intelligence. And so we talked about it over lunch and then we gave up. But in 2004, this idea got picked up again because of something called the World Year of Physics. And the American Physical Society offered to try and do some publicity and get volunteers. And we got connected with David Anderson, who got me excited about BOINC. And so we launched Einstein at Home in 2005 and have been running it for 16 years now. The goal of Einstein at Home is to find neutron stars via their electromagnetic and gravitational wave emission. And what you see on the screensaver is actually a distribution of constellations, but also locations of some of the known pulsars and the supernova that they came from. Many people have contributed to Einstein at Home over the years. I've listed just some of them here. Oliver Bach, Bernd Machenschaft, I think, are both on this call. They've helped a lot over the years. And this has been supported both within the United States by the National Science Foundation and in Europe through the Max Planck Society. Neutron stars were discovered by accident in the summer of 1967 by Jocelyn Bell, who was a graduate student at Cambridge University. She was working at Mullard Radio Observatory, doing observations that were intended to study atmospheric scintillation. She wasn't actually using the radio dish that you see in the background, but something a little bit less glamorous that she and some other students had built over the summer. And she found in August 1967 a strange repeating signal. You can see it marked on the strip charts on the plot here. And this repeating signal kept reappearing every day, but not synchronized to Earth time, but synchronized to sidereal time, which differs by 4 minutes. And so you knew it had some sort of non-terrestrial origin, but didn't know what it was. And she and her advisor, Anthony Hewish, went through lots of different ideas, including little green men, and eventually realized that what they'd observed were signals from some very compact kinds of stars that were actually proposed by this guy, Fritz Zwicky, and a collaborator of his in 1934. That was just 2 years after the neutron had been discovered experimentally. And what they had predicted then might happen is that when stars run out of fuel, stars burn fuel. They don't burn carbon with oxygen the way that we burn fuels on Earth. They instead burn nuclei. They combine light nuclei and make heavier nuclei, and they get out energy that way. But what happens is when they have burned the light nuclei into heavier ones, they stop producing light. And if the stars are massive enough, they collapse. And when they collapse, they can form what is effectively a gigantic atomic nucleus. And this is what had been discovered. This is an animation that shows why Jocelyn Bell saw this flashing signal. She was seeing a very compact object, a star, that was spinning about once a second, and it was emitting electromagnetic radiation in a beam, like a lighthouse. And when that beam swept by the Earth, there was a pulse. These objects are called neutron stars. They weigh more than our sun, typically about 1.5 times the mass of the sun. They're extremely small, 10 kilometers in size, and they can spin very fast, 40,000 RPM, so faster than any automobile engine. The material in these objects is so dense that if you had a teaspoonful of it, a sugar cube, it would weigh about as much as a mountain on the Earth. They have very strong magnetic fields. They emit radio waves, light, gamma rays. They should also emit very weak gravitational waves, but we've never observed those. And as of yesterday, I looked in the Australian Telescope National Facility online catalog, there are 2,872 of these objects that have been discovered. They're really very cool because one way to think about them is it's the closest that you can get to a black hole before you actually form one. And they're used to study extreme states of matter. They provide some of our best tests of general relativity. They might provide a way of doing detection of long wavelength gravitational waves. In short, they're just very neat objects. So Einstein at home is looking for new neutron stars. And I'd say that we're an unusual BOINC project because we use data from instruments. We use real world data. And the data that we analyze comes from gamma ray instruments. You see in the top left there, the Fermi Gamma Ray Telescope, which was launched more than 10 years ago. We get data from radio telescopes. You can see the Arecibo telescope there. This is before Arecibo's accident. But we're still analyzing data that was taken several years ago from Arecibo. And the bottom right is Meerkat. That's a new radio telescope that's in South Africa, which we're going to start looking at data from. And in the bottom left corner there is the LIGO instrument, which is a gravitational wave detector. So we take data from these different instruments and we search it for spinning neutron stars. Now, our universe is a really big place. It takes light 14 billion years to get from one side of what we can see to the other side of what we can see. And the neutron stars that we can detect are really very close by. They're in our neighborhood. What you can see here in the background is something like what our galaxy looks like. And it takes light about 100,000 years to get across our galaxy. So it's very small compared to the universe. And we don't live in the interesting high density neighborhood by the X. That's the center of the galaxy where there's a lot of stuff happening. We live in kind of the boring suburbs out in one of the outer arms. That's what the green arrow is showing. And the neutron stars that we've found so far, these 2,800, are pretty much near us, because as they get farther away, they get harder to see. The signals get weaker and they get blocked by dust and other stuff. But in our galaxy, just in our galaxy, we think there's about 100 million neutron stars. So we've really only found a very small fraction of what's there. And one reason is because finding them is a difficult data analysis problem. I'll show you a little video that's meant to explain why. So imagine that, I'll start the video in a second, but imagine that you're looking at a lighthouse by the ocean and the lighthouse is flashing maybe every 2 seconds as the beam sweeps by you. So if you look at that and somebody says, how often is it flashing? You just take your wristwatch and you look at a flash, or I guess your cell phone these days, and then you wait a couple seconds, you measure the time, and you can say, that's flashing once every 2 seconds. But now imagine that you go far away from that lighthouse, far enough away so that you don't see every flash because the light doesn't reach you. The photons just don't arrive in your eye. So if you get far enough away, maybe you see one flash out of every 10. And if you're clever, you can take the time between the flashes and figure out how long it is. But now imagine that you move even farther away so that you only see one flash every day. Then it gets much harder to say, how rapidly is this lighthouse flashing? So let me start this video. What we're doing is we're looking at different points in the sky and different points in parameter space at a set of photons. And we say, suppose the neutron star is spinning this way. And we kind of line up the photons according to how far the star has spun. You can see 2 rotations here. And most things that we try, you get no pattern because we've got the wrong parameters. We've got the wrong spin. We've got the wrong sky location. There's another one where we didn't get it right. But eventually, if we find exactly the right combination of parameters, we try it out, and suddenly we get a pattern. You see the pattern there? That's the peaks in the lighthouse, which we figured out. In this case, this is several years of data with an object that's spinning 100 times a second, and yet over a course of years, we only have a few thousand photons. So that's the reason why we use a lot of computing resources, because it's a very difficult data analysis problem. Now, one of the things I'm proud of is, to date, Einstein and Holm has found about 80 new neutron stars. We've published about 20 papers from this. And if you look on the Einstein and Holm website, you can find out a lot more about this. We have a link to our publications, and we also have a link for our discoveries. All the Einstein and Holm publications are open access. And I don't think in this very short talk, I'm going to try and tell you about all of them. I will just pick out one just to give you some flavor for it. One of the things we do is, when one of our participants finds a new neutron star, we send them a discovery certificate. And if you look very closely at these, you'll notice a couple of things. One is that very faintly in the background is the pulse profile of that pulsar, the neutron star that they found, which is a very distinctive signature. It's kind of like a fingerprint. The other thing is that this is in 2 languages. We always send 2 of these certificates. One of them is in the native language of the person who made the discovery, and the other is in English. We figure one's to hang at home and one's to hang at work. And so far, we've had to do these in 20 different languages. So we really have a user base that's spread around the world. Well, I wanted to close by just showing you one of the discoveries that we've made quite recently and published. This is kind of cool. It's an object that's called a black widow pulsar, and I thought I'd explain what that is. So this was found in data from the Fermi Gamma Ray Observatory. And you can see here in my slide both the paper itself. You notice, by the way, in the top left corner, it says open access. So anybody here who wants to read this can do so. And on the right-hand side, you can see this plot that shows a couple of thousand photons that arrived over the course of about 10 years. And with that, we were able to find an object which is spinning about 500 times a second. So really a remarkable challenge to identify the rotations when there's a billion rotations in between every photon that arrives. By the way, the people whose computers found this, one is in Taiwan, the other is in the US. And this pulsar, to me, was a very special thing to find, because the source of gamma rays, it's a bright source in the sky, which has been known for a long time. It was first seen by an observatory, a satellite called EGRIT, in 1999. And it was actually the brightest unassociated gamma ray source in the sky until we finally figured out what it was. And this object, I'm going to show you another animation, is a neutron star, which is orbiting another star. And so what you'll see in this video, the neutron star itself is that little tiny bright spot in the corner. And the thing that it's orbiting is about 1 million kilometers away. And what happens is the neutron star is emitting such a powerful beam of radiation that it's actually evaporating the companion star. So that companion star weighs about 10 times as much as Jupiter. It's about 1/100th the mass of our sun. And it's actually being vaporized by the pulsar. And this is called a black widow because supposedly black widows, after mating, the female eats the male. So in this case, the pulsar is actually destroying the companion. Okay, well, the last thing I'd just like to talk about for a moment is the motivation for why we started Einstein and Holm. And it actually has to do with gravitational waves. And this is the most ambitious search that Einstein and Holm does. We would like to find the gravitational waves that are emitted by spinning neutron stars. Now, gravitational waves have been one of the holy grails of science for 100 years. And they were successfully first detected in 2015. A signal was seen from the merger of two black holes. And you can see here that made the front page of the New York Times. And since that time, we've seen about 100 similar mergers. And that's a very brief gravitational wave signal that lasts just a fraction of a second. We'd like to find gravitational wave signals emitted by little mountains or bumps on spinning neutron stars. These would be continuous. They wouldn't be a little burst of radiation. They'd last a long time. And we've been searching for them with Einstein at home now for 16 years, and we're going to continue that search as the data gets better and as our search methods get better. I'm optimistic that we will eventually find something, and that will be very big news because that will be a new source of gravitational waves and will be another New York Times front page story. Thank you.
Thanks very much, Bruce. Looks like we have quite a few little applause hands for you. Has anyone got a question for Bruce? Marcus has a question. Hold on one second.
Hello again.
Hi.
The side has got me up. I might go to sleep after this one though. But I did want to ask you a very interesting and slightly funny question. Is it true that the scientists at LIGO actually kick the detectors to make sure that the instruments are accurate and working correctly?
Well, I can tell you, Marcus, that our first gravitational wave detection on the 14th of September, 2015, it happened at the LIGO instruments in the middle of the night. It was I think coming up to 1 o'clock in the morning in Washington State, and it was I think 3 or 4 o'clock in the morning in Livingston, Louisiana. And we were very fortunate because at the time in Washington State there were just a handful of scientists on site, and what happened is the last ones who left had planned to do one last experiment before they left, because this was before our first science run began. They wanted to drive a car over a speed bump in the parking lot. The thing is that before they did that, because that shakes the ground and shakes the instrument, and they wanted to just record what the effect of that was, so they had a record of it. But they wanted to do that at a very precise time. And they normally use a GPS synchronized clock. So they drive over the speed bump at a very well-known time. And their GPS clock had lost synchronization. They decided that was a sign that it was time to wrap it up and go home and get some sleep. And we're very fortunate because if they had driven over the speed bump, that sometimes just knocks the instrument out of lock. It stops working. And that was a rather short time before this first signal arrived. So the answer is yes. They disturb it often by doing things like driving over speed bumps, and we got very lucky that first time around that it didn't happen.
Wow, fantastic. Thank you for that.
You're welcome.
So we've got another question here. Someone who's identified themselves as Mr. HH. So you are now on.
Okay, thank you very much. I'm from Holland,
Hi.
Amsterdam. My question is actually, so how do you credit academically? So do you make the people who are kind of part of this project a co-author, or how do you do that?
There's many different levels of contribution. There are Einstein at home volunteers who we've hired who now work for us because they were so good. There are people who have done rather remarkable things in profiling and rewriting some of our code to make it faster. Those people are acknowledged or in some cases have been made co-authors of papers. The volunteers, we always acknowledge in the acknowledgement section of the paper.
Okay.
They're not co-authors though. So we do try and recognize people who've contributed to us. So I hope that answers your question.
Yeah. No, I think that is one of the problems I see, because that is one of the issues you always have with scientific publishing.
Yeah, it's our impression that volunteers are motivated primarily because they want to make some contribution to science. That's one motivation. The other motivation is because they have really cool computers and they want to see what they can get done with those. So the fact that they are not co-authors, for example, on scientific publications, that's not so important to them. They're happy just to get some recognition and a cool certificate.
Okay.
And by the way, the certificates really are cool. So for example, the discoveries made with gamma ray observatories get signed by Peter Michelson, who's the person who led that project, and by me. And we actually send these things around. That's not a digital Photoshop signature, it's the real thing.
Okay. Okay, thanks.
Great. Well, thank you very much. Let's see. So, Bruce, I've got a quick question for you, actually. You mentioned that these pulsars you're measuring rotate, well, there was one that was rotating very fast, like 500 rotations per second or something, you said, or per minute. In my head, I always figured stars were quite large. And so that seems to me staggeringly fast. So how big are these things, and how fast is the surface of that thing going as it spins? Hold on a second. Oh, you became muted. Hold on.
Thank you. Yeah, it's my own fault. I clicked the wrong button. It's remarkable. So Matt, these things actually boggle the imagination. I mean, think about the following thing. A really fast car engine spins at 6,000 RPM. If you want to store electrical energy, for example, as a backup power supply, one of the ways of doing it is you take a flywheel made of metal or ceramic or composite material and you spin it really fast. If it weighs 50 or 100 kilos, it stores a lot of energy in that motion. What we have here is an object which weighs more than 1 million times what the Earth weighs. It's about 10 kilometers in radius, and it's spinning at, the fastest spinning one is spinning more than 700 times a second. So that's more than 40,000 times a minute. You know, it's 40,000 RPM. The amount of energy that's stored in something like that, for example, I mean, you know, what is it in Star Wars? The I forgot now. What's the name of the horrible, destructive thing that, you know, vaporizes Darth Vader's toy? Vaporizes
Death Star.
planets. The Death Star.
Yeah.
Okay, you look at the amount of energy it would take to vaporize the Earth, and it's much less than the energy that's stored in one of these spinning objects. Much, much, much less. Okay, so the Death Star is a child's plaything energetically compared with one of these.
I'm not sure if that's encouraging or not.
Well, you know.
But that's really cool. Thanks. So any last questions for Bruce, or?
I can answer the one that I see here just briefly. So LIGO's data, the gravitational wave data, LIGO is sensitive to what are effectively audio frequency gravitational waves. So gravitational waves with frequencies from about 100, let's say 20 or 30 hertz up to a few kilohertz. So it takes samples at 16,384 samples a second. The Nyquist frequency is 8 kilohertz because that's perfectly fine. Now the angular resolution is absolutely terrible. Each LIGO instrument is a quadrupole antenna. So it sees basically the entire sky at once. It has absolutely zero angular resolution, in the sense that the angular resolution is about 180 degrees, maybe 90 degrees. So the only way that we get any pointing information with LIGO at all is because there's 3 of them. There's 2 in the United States and there's 1 in Italy. And together, those 3 instruments can triangulate to find objects on the sky. Otherwise, we'd have no idea where the sources were at all.